This video is about Drake's equation, which is a probabilistic argument used to estimate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. Now, before I get into the details, I just have to say that all the information that you see on the whiteboard is extracted directly from Wikipedia, and I have not added anything or taken anything away. And if you go to the entry for Drake's equation on Wikipedia, you can extract this or look at this information probably in the first couple of sections, first one or two sections for the entry. Now, this is originally the equation was formulated by Frank Drake, and the year was 1961. So the mathematical model has been alive for a while. It's beginning to evolve. As you can, when you go to the entry, you'll see individuals like Seager who have taken Drake's equation and have successfully applied it. Sorry, I gotta close my laces. And they've successfully applied it towards finding exoplanets. So what Sarah Seager did was she took Drake's equation and she hacked it, for lack of a better word, in order to be able to find gas signatures on exoplanets. And doing so has led to, I believe, an increase when it comes to finding exoplanets using this slightly different development. And has, that's a very interesting thing that has happened in the past couple of years. There's a Google talk, I believe, of Sarah Seager. It's about an hour long, where she talks about the rudimentary framework of how her equation works, which is called Seager equation, if I remember correctly. Well, when I'm going to talk about Seager equation, I will delve a little bit into just scratching the surface of what Drake equation is. And let's begin. So the entire combined expression for Drake equation can be like summarized with this equation right here, this part right here. This is not working. So this is the combined expression, and N indicates the number of civilizations that I began with, and N is a collection of the following variables, and we're going to talk about what these variables are in a couple of seconds. But in case my daughter's watching this, like the child's watching this, so again, this is a probabilistic argument. It doesn't mean that it's true. So probability means that if you have a total number of outcomes, and then you want to figure out the probability, then what you do is you take what you know, and you take the total number of probabilities, and you divide what you know with the total number in order to be able to come up with a probabilistic model. I think this is how you determine probability. This is the simplest way of determining, simple probability, that's what it's called. But probability is another topic which I don't understand very well, so I'm not going to talk about it. But again, this is a probabilistic argument. It is not a it's not a equation that's set in stone. At least I don't think so. And it's the model is used to estimate the number of active communicative extraterrestrial civilizations in the Milky Way galaxy. So before I get into this, going through this and explains like the rationale. But again, this is a probabilistic model that is used to estimate the number of active communicative extraterrestrial civilization in the Milky Way galaxy. I'm probably repeating this a couple of times. Extraterrestrial means something that is outside the bounds of terrestrial habitats. So terrestrial would mean relating to Earth, and extraterrestrial means outside of Earth. So if we happen to find life on Europa or Mars, like even if it's bacterial life, technically speaking, it is actually extraterrestrial life. If you find life or some other object, even inanimate objects on another planet, then again these would be considered extraterrestrial. Civilization is, what's the good definition of civilization? Civilization is all around you. We live in a civilization. I haven't looked up the actual definition, but to me it would mean a collection of activities slightly intelligent beings perform together in order to be able to advance their cause or their survival. You can have primitive civilizations, you can have advanced civilizations, you can have technologically advanced civilization, and they all kind of sit on some spectrum. I think the Kardashev scale is a good model of categorizing the evolution of civilizations, but we're not going to get into that debate today. So that being said, hopefully that explains what Drake equation the intention is in terms of the mathematical model. So let's get to the combined expression. So again, n would be the number of such civilizations, and we're trying to come up with a number. So Frank Drake thought of this combined expression in the 60s, whereby R with a asterisk or like a star sign this should actually be right here. Sorry. Where R is the average rate of star formation in our galaxy. So for those who may not know, if we are here, say this is our solar system, and we have, I don't know how many planets we have now, I should know this, but we have all these planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Pluto is not a planet, but I think we found another one, smaller one. But anyway, so if this is our solar system, so our sun is here and all these planets are around in a heliocentric orbit, then let's represent our solar system with a dot. And the planets are going around the sun, but there's actually 100 billion, if I remember correctly, such stars around the galaxy. So if we were a speck, then there's 100 billion such solar systems or suns. We don't live in a sun, we live in a solar system. And apparently there's a black hole in the middle that's keeping everything going, from what I understand. I haven't seen a picture of one yet. If you find one, let me know. No, I'm just joking. We haven't made an actual, taken an actual image of a black hole, but there's a high degree of probability that one exists, or all the galaxies are going around black holes. But yeah, so we have all of these suns, and we have the black hole, and that's a very rudimentary picture of what a galaxy may look like. You should actually Google picture of galaxy. They're of different shapes. Some are colliding, some are of different shapes, but that's kind of like one way of kind of looking. If you were looking at it from another angle, it would probably look like this, with like each one of these bands representing a star. I don't know if actually galaxies look like this, but based on the spectral analysis, that's what we can see. So our galaxy, the galaxy that our solar system is part of, is called the Milky Way. And it's called the Milky Way because when you look up at the night sky, there's a band that kind of goes when there's not a lot of light pollution. Maybe if you go up north or outside of the city where there's not a lot of lights, and you can look up at the night sky and see a band of like stars across the horizon or in the sky, and you can kind of get the tail end of, you can see like like the galactic structure of all the different stars that make up our galaxy. So coming back to the equation, R is the average rate of star formation in our galaxy, because we're talking about the Milky Way again. And I don't know much about star formation. I know that it's happening across the galaxy all the time. So you have an accretion of dust and rocks that have been kind of bubbling, or sorry, not bubbling, bouncing around the universe since its beginning. There's a certain number of processes that are responsible for star formation, which again I don't understand, so I'm not going to talk about it. But stars are getting created all the time. The stars are actually dying all the time across the galaxy and the wider universe, potentially multiverse. But in terms of Drake's equation, this is what determines the rate of star formation in our galaxy. So what is the rate at which new stars are getting formed? The next one is F into P, which is the fraction of the formed stars that have planets. So like I was referring to earlier on, that not all stars may have planets around them. But the ones that do would represent this. Well, I think that's pretty much explains itself. Yeah, there are different kinds of stars, and the sun is a star. So yeah, there's different sizes. The sun that our planet goes around is actually one of the smaller sizes. There's some suns or stars out there that are, like, compared to our sun, are huge. It just happens to be the case that our solar system it's got the right kind of conditions, the right kind of sun. Then we've got like these gas giants, which are actually quite, they play an important part when it comes to sustaining life on this planet, or have the probability of life evolving on this planet is because of a variety of different reasons, based on what we know so far. But yeah, so the sun, the size and like its place in the galaxy, like all these things, and like other planets in the orbit, they determine the probability of life. So we're not getting into all of that, but just kind of sharing that. Again, not all suns or all stars have planets around them, but the ones that do would be, in the equation, would represent by this. N into E would represent, for the stars that have planets, the average number of planets that can potentially support life. So I think that pretty much explains itself. But and I was kind of building up to this, I guess, unconsciously. So you need the right kind of environments based on what we know in order for life to be supported. The theory has been that you need water, you need carbon, and you need a couple of things in order for life to be able to sustain itself. We've made at least one discovery in the past 15 years whereby we found bacteria that can ingest arsenic in, like, really, I think it was somewhere in British Columbia that NASA actually made this discovery, from what I understand. But I gotta bend down in order to be able to make this video, because otherwise it's gonna be too far off. Hopefully, like, you can see all these. I can make it a little. I don't know if I can do this. But you have life forms that can ingest arsenic, which is a poison, and they can, these bacteria can still survive. So who knows what kind of life exists out there, if it is organic, if it really needs oxygen and water and all these other things. We don't know, but based on what we know and based on what we see around our planet, water is one of the things that pretty much all the life form on this planet is dependent upon. So we're kind of, I think we kind of use that model and we try to extrapolate the probability of life elsewhere. I may stand corrected on some of the other things. I said oxygen, but I was with the other example of the bacteria, I was trying to counteract that. But that's based on what I know, and I could be wrong. So if I am wrong, make sure you leave a comment and let me know message me on the comment section below. So next up is F into L, which is the fraction of those planets that actually develop life. So there's the right kind of conditions in order to be able to support life, but then even though those conditions may exist, there is no the probability that life actually evolves is codified with this next kind of section. So the right kind of ingredients come together in order to be able to develop life. And based on what we know, what has happened on our planet is that a long time ago, amino acids interacted with the electricity in the atmosphere in order to be able to support the basic building blocks of life. And then the interactions happen over a period of time, or a long period of time, because evolution changes over time, and evolution is a very slow process. So if you may see things around you, and you might see things that change really fast in the past 100 years compared to a lot of technologies and tools we've developed. But when it comes to life, the evolution of life it's a very slow process. And I think the Earth has been in existence for 4 or 6 billion. 6 billion years. So that's a really long time compared to the life of our biological bodies in this era, the life of even civilizations. You can have an entire civilization rise and potentially fall for maybe 100 years, 200 years, 300 years. And that's based on our knowledge so far. But what I'm trying to get to here is that the lifespan of planets, the universe and the components within it, like suns, planets, and other things, is on a potentially larger scale. There's obviously exceptions to that rule. But generally speaking, if all of this surface area of the whiteboard represented the formation of the universe, say from here, whoops, can't really see it. Yeah, so like starting here, Carl Sagan does this really well when he kind of makes a calendar in Cosmos, the original series. I don't know if Neil deGrasse Tyson did that as well. Like there's a calendar and there's the 12 months, and then he shows this is the Big Bang and all this time passed, and here's the pyrocorites, that's when they evolved and they turn into eukaryotic life form here, and all the way down in the end, like this in tiny, tiny corner, all of the things that we know can be summarized on a single, not even a single speck, like a really, really tiny arrow. So what I'm trying to say is that time and our perception of time is like we have a perception of time going fast or slow, but in universal terms, time, things take a long time to, generally speaking, for life to evolve and all these things. So going back to the equation, for the right ingredients, for them, like the right series of steps to take shape and be able to actually develop life is what is represented by F into L. Next up we have, just making sure the video is still recording. Next up we have F into I, which is the fraction of planets bearing life on which intelligent, civilized life has developed. Alright, so I think this is an interesting point because intelligence is relative. Because if you look at our closest biological ancestors, I think that would be the chimpanzee. And when you look at the genetic code between, say, like, I'll try to do a rudimentary drawing. So like a human, and you look at their DNA, and then you look at a, how do you make I don't even know how you make a chimpanzee. But you have a chimpanzee, and all right, let's make a tail and make some legs. All right, and you look at the chimpanzee DNA. 99% of it is the same. Is exactly the same. 1% is different. 1% of our DNA is different. So we share, if this is human, this is chimpanzee, we also share DNA characteristics with horse, the potato, a bunch of other things that sound like a robot. And you make these examples, I always make these, leverage these examples. But that 1% of the difference, this will pop up here. That 1% of the difference gives us everything that is around us. It gives us the tools that we've created, the spaces that we eventually created with those tools, the culture, the language, the technologies, which is a form of a tool, arts, sciences, civilization. All of these are the result of the change when it comes to that 1% different in DNA. And I want to get into the conversation of how that DNA actually impacts cognition, like language, like all these other things. It's a longer debate, which I don't know much about anyways. But what we have to appreciate is that 1% of the DNA is what separates our kind of like Homo sapien subspecies from the closest ancestral relative in a biological sense, which is chimpanzee. And it's based on intelligence because it's something innate about the neocortex, which is part of the brain of the humans, which gives them us the thinking ability to be able to do all these things, which again separates us from chimpanzees. Intelligence in that respect is a very broad spectrum. There could be levels of intelligence which is going to be difficult for us to be able to wrap our minds around, considered like a relatively limited cranial space and the ability to be able to form mental model and really be able to wrap our mind around such realities. But it's the same analogy. Just like if you take a chimpanzee and you try to teach it computer science and like this is how the water system works, and maybe it is able to understand all these things. Probabilistically speaking, not. I mean, the probability is pretty low that the chimpanzee is going to be able to wrap their mind around all of these things. They don't have the gene which allows them to communicate on our level, and it doesn't look like they have the ability to be able to do some of the other things. They are better at some of the things like short-term memory, and even short-term memory leverage for, believe it or not, mathematics. Chimpanzees, other subspecies in the primate arena are pretty good at that. In fact, they're better than humans. They beat humans when it comes to cognitive tasks on a short-term basis, like really like short-term. This is on YouTube. You can look it up. But intelligence is a conversation by itself. But what we're going is with a very, simplistic definition of the fraction of planets bearing life on which intelligent, civilized life has developed. So I should have probably looked up the definition of civilization, but civilization in this term would mean like instead of actually being dependent on whatever has evolved for on the surroundings for like a long time, and being dependent on just in your surrounding and your kind of like a hunter-gatherer society would be an example. Is a hunter-gatherer society civilized? It's a good question. I don't want to get into the specifics, but I guess a shorter definition of the creation of tools and the ability to be able to modify your surroundings and come up with some kind of a codified mechanism to really able to sustain your well-being and your safety and security, and prosper, I think, would be a definition of civilized life. Again, this area is kind of up for debate, but these are my thoughts. This is not Frank Drake's or anybody else's commentary. So you should probably keep it more simpler. Next up is F into C, which is the fraction of these civilizations that have developed communications. That is, and it continues, technologies that release detectable signs into space. All right, so this is interesting. So this portion right here signifies that civilizations have developed a means of communications which are then released into space. So I'm guessing that the time when Frank Drake came up with this equation in the 60s, radio was the predominant technology, probably television at that time as well. The ARPANET was probably a secret project at that time, because I think it was around the mid-60s that President Kennedy presented the bill for ARPANET to Congress, and it was in I think a budget of a couple of tens of millions of dollars. But what I'm trying to get to is that Frank Drake, when he was coming up with that with this equation, he was probably thinking in terms of the fact that there's radio and there are these waves, and the waves get disseminated through the medium, which on our planet is the air. Radio signals don't really need air, but at least I don't think so. But he was like, and eventually what happens with these waves is once they kind of bounce off and whatnot, they go beyond the stratosphere or the orbit and out into the wider universe. I think the waves do get scattered, so the signal may degrade at some point. Probably getting into too much of a detail, but this part is probably coming from that mindset that if civilizations are to develop technologies, then it's going to go through some medium, and some of these signals will eventually get released into space, which may or may not be true. There's no again, this is coming, I think, from the historical context. Advanced beings may create communications or platforms which are leak-proof, so to speak. So that's also a possibility. So this one, it's a little all of it kind of makes a lot of probabilistic sense. This one I'm not personally too sure about, but I'll keep it that. So last of the last bit when it comes to the combined expression is the letter L, which signifies the length of time over which such civilizations release detectable signals. Again, building up on my previous comment, I'm not too sure that's going to happen on a continual basis, because the thing with technologies is, generally speaking, it looks like based on our own evolution, or at least the history of civilization from the perspective of the past 10,000 years, we kind of build technologies on top of each other. And generally speaking, because of the curves, there is a increase when it comes to the quality and the output in terms of efficiency and whatnot. And you just end up building better, and you combine different things together and it will power newer forms. So this is where my commentary starts. I guess it was happening all along. But these two parts I'm not too sure of. This is actually my first attempt looking at Drake's equation in this much detail. I would have to think about this a little bit more in order to be able to further ascertain what, in my opinion, needs to be added or modified, or what can be extracted from this model in order to be able to apply the combined expression in other domains, not unlike what Sarah Seager has done. Now I should, before I carry on, I should mention, and this is again directly all this is, except the part where my commentary was added, most of this information that you see, 100% of the information that you see on the whiteboard, as it is, not my commentary, is directly from Wikipedia. And originally, when Frank Drake came up with this equation, the original rationale was to stimulate scientific dialogue at the very first scientific meeting for SETI. And SETI stands for the Search for Extraterrestrial Intelligence. It is an organization that has been in existence, since the 60s. I actually used to, SETI had a program for distributed computing, whereby you could download data from their website, which was a collection of data they collected through their radar system. I think the intent was to find the signal and the noise. So there's all this static in space around us, coming from all sorts of different directions. But I think there's a specific signal that SETI is looking for, and so you have a lot of data. How do you process it? Well, you break it in chunks and you send it out to computers around the world. So SETI started that project. It used to be called BOINC, B-O-I-N-C. I have no idea what it stands for at this point. It's been a while. But I used to contribute to that project by donating my computer time. And it's pretty awesome to see SETI is still going strong since the 60s. In the past 15, 20 years, there has been donations made by, I think one of the founding members of Microsoft made a big donation to keep the organization going. But this is a part of what constitutes basic research, and SETI has played, and I hope and believe will continue to play that pivotal role. But again, so going back to the rationale, that's just what I know about SETI. They could be doing a whole bunch of other things. But again, the original intent was to stimulate scientific dialogue, not just like philosophical or wishy-washy kind of dialogue. Not saying that's bad, but scientific dialogue at the first scientific meeting for SETI. So, not knowing much about the scientific principle, I will reserve my thoughts. But search for extraterrestrial intelligence. Intelligence outside of our terrestrial habitat, outside of Earth, any noticeable signs. There is at least one organization that has been dedicated towards not just thinking about these things, but actually doing something, taking action in order to be able to further that cause. I believe this is absolutely very important for us and as a species. And there's two schools of thought here, at least. One is that we are alone. I shouldn't start with that. Let's take a step back. There's two possibilities. One is there's from a simple probabilistic model, like the simplest probabilistic model that you can come up with. Actually, there's not two. There's three, I think. So the simplest probabilistic model is, just gonna move this a little bit. So the simplest probabilistic model is that there are other advanced civilizations out there, and you can kind of make a spectrum whereby the evolution of those civilizations would sit on some particular point at that spectrum. Realizing very well that from a cosmic perspective, even 100-year time frame is enough for radically different changes to happen. I mean, if you kind of go 100 years, we as a species didn't even have basic sanitation across most of the major cities. We still don't on a 100% basis, but at the same time, we didn't. I don't think we had winged flight 100 years ago, but if you fast forward 100 years, we went from like this reality whereby a lot of these things were not possible to today we're taking rudimentary steps, actually quite concrete steps, and we're able to get to Mars. So we're getting from one rock to another, which is quite a momentous occasion for any species. If you can make the leap from your original planet, which we evolved on to the best of our knowledge. Although I made a video about panspermia theory. I'm not going to get into my other theories, but making this leap from one rock to another, that's quite a momentous occasion for any civilization. If there was some kind of a ledger on a galactic scale, that would be a huge check mark. That's like, all right, that's, you know, what other things are they doing? Are they growing their food sustainably? What about energy extraction? Are they still digging up dinosaur remains? Yeah, so like that would sit on some kind of a spectrum, right? And I was getting to the 3 points. So either there are civilizations out there and they sit on some kind of spectrum when it comes to level of intelligence and how that kind of manifests in terms of technological development, which is then depending on certain principles. So we have a principle that humans have developed called a scientific principle. There could be others out there. There could be something beyond mathematics in a Brian Greene sense. So not getting into that debate, but that's the first spectrum. That advanced civilizations, based on their level of intelligence, sit on some spectrum right here. The other probability is that there are no other advanced civilizations. That there's maybe life, but for some reason, it's a very rare phenomenon, and it is all hypothetical, at least from a scientific, at least from a very kind of using reason as a construct. But the other probability is like there are no advanced civilizations. We are the only advanced civilizations across the 100 billion star systems across the entire galaxy. And then you have 100 billion of these galaxies, potentially more, with the finding of the gravitational waves. Because we're doing spectral analysis, and that's all the stars we've mapped, and we have these probabilistic models. But they're even considering this enormous universe, not getting into the multiverse theory, but even considering all these numbers, the probability of life evolving and getting to an intelligent level is very rare, because gamma ray bursts are more frequent than we can measure, or maybe there's some other weird set of cosmic phenomena whereby, again, the probability is low. So these are at least the two probabilities that either there is intelligent life and it sits on a spectrum, or there is not. There are other theories, such as the transcension hypotheses, whereby, the way I understand it, whereby advanced civilizations, I'm not going to do a good job explaining this because I've only read the Wikipedia page once. I don't even know if I completely read the page, but you have advanced civilizations and they want to compute on denser scales because it's, from the perspective of energy, it's more efficient, or for some other reason. So the transcension hypothesis states that advanced civilizations go, and like, I don't know how to explain it, but instead of going outwards, and like Carl Sagan said, civilizations either become space-faring or they become extinct. So that's Carl Sagan. But the transcension hypothesis states that, or it says that there's plenty of space at the bottom. No, that's what Richard Feynman said. But that's what transcension hypotheses is, the way I understand it. That like advanced civilizations or beings choose to go on a smaller, denser scale so they can compute that much more optimally. I think that's the definition. I don't know. So those are three possibilities. There may be other possibilities. There's a whole bunch of theories. It's possible that at a certain level of technological advancement, a species may find out that there's more risks associated with inhabiting a particular galaxy for any given reason, and they may choose to inhabit another galaxy. I don't really know how this is going to happen. My understanding of physics is non-existent, so I'm not going to talk about wormholes and all this stuff. But how that would happen. There's another possibility whereby an advanced species may choose to go into a kind of like a hibernation mode of sorts. I don't know what this is called, but I read an article on IEEE, which is the Institute of Electrical and Electronics Engineers. I'm not an engineer by trade, but this article states that at a certain technological development, there's a possibility that there may be a possibility that there's advanced species within our galaxy that may have gone into the hibernation mode of sorts because they want to compute some problem, and what they would do is they would have computation. So this is making a lot of assumptions that computation has to be destructive. So you get into that comes in like destructive versus non-destructive, or reversible versus non-reversible computation. But this particular theory states that after this species or civilization goes into hibernation mode, they have kind of like what's the word? I'm getting tired, I guess. They've created these constructs and are able to maintain their systems and even their defense, dealing with some unknown potential situation, because they don't want to be waking up from their hibernation till that problem is solved, whatever the problem that their computation engines are solving. And they are doing this. Again, it's based on hypotheses, I believe, that this is a destructive form of computation which releases energy as a byproduct. So what they're doing is, the theory goes that these advanced civilizations are living on the periphery of the galaxy, because they use the deep space or the area outside of the galaxy as a massive heat sink for all their computation. So it's kind of even like, it's like I don't even know how to wrap my mind around what kind of what level of technological sophistication would be required in order to be able to power such a reality. But it may be possible. Is this like, unless you've actually been able to peer and scan the different galactic portion of the galaxy, you cannot disregard that such a reality may now exist. These are the four that I can think of at the top of my head. I could probably think of a couple more, but I don't want to take up more time. My personal take, knowing what I know about, this much I know about, whatever I know about, I think the probability of life existing within the galaxy and many other galaxies is huge. I think that life is very predominant. And I've made a video about the panspermia theory, which is not to say it's the only theory, but I think the probability of life emerging in different surroundings is very high. My personal guess is that areas where there's water, even if it's liquid water under the surface, that life has a very good chance of evolving. Because you just go look around the world planet and you see like these crustaceans or shrimps, they're evolving like 10,000 feet under the ocean near volcanic vents. So they're using that as a heat or energy source. And never in contact. They're never, like, it's very low probability. Maybe they will evolve to advanced beings in, I don't know, like 100 million years if the climate doesn't change or anything. But probabilistically speaking, I don't think that's going to change much for crustaceans. Who knows? Who knows? But like, so you look at things like that. You look at how bacteria is the predominant life form on this planet. There's bacteria under the soil. It's in the oceans. It's around us. It's everywhere. It's in our bodies. We have more bacteria than our number of cells in our body. So look at things like this, and like the fact that there's a bacteria that can eat like arsenic, which is poison, and still be able to recreate or reproduce itself, or however the production happens, asexual or sexual. So like, just these are just three of the many examples. And like going back a couple of billion years, there was a time when life, cell reproduction, making a copy of itself. So that's before we were a eukaryotic life form. So that, like, there's all these different things, just like this, just based on what I limited knowledge, probably is pretty high that there's life out there. The question is intelligent life. And my uneducated guess is that there is intelligent life out there. Depends again on how you define intelligence. I would say that a chimpanzee, and how we observe it today in our surroundings, is intelligent because it has the ability to do rudimentary tasks, like I said, some even mathematical tasks on a short-term level. And it has the ability to be able to convey its thoughts as rudimentary as they may be. And is able to do a bunch of other things which are, it cannot be just disregarded as unintelligent. And I think there may be a reason why we classify beings that are not human as unintelligent, but I'm not going to do that debate. But even like if you look at dolphins, or what else? Some birds, they can mimic humans, even their voice and sounds quite well. So we see signs of intelligence all around. And from an evolutionary perspective, this is the remnant of how life has evolved for a long time. And it's a snapshot. And even within this in this enormously diverse snapshot, which is just a tiny remnant of how life has evolved on this planet for billions of years, we see signs of intelligence. So what I'm extrapolating to is the probability that the probability of intelligent life existing in this galaxy, in my opinion, in my uneducated opinion, is that that probability is high. And I have my own theories. I think that there's truth to the panspermia theory. And if life, in fact, is being seeded from planet to planet across the galaxy for billions of years, then there's got to be intelligence out there. The question is, how is it intelligent? To which scale? Where does it sit on the spectrum? There's something called the Kardashev scale. I think that's how you say it, Kardashev scale. Nothing to do with the Kardashians. Hopefully not. At least, hopefully. But yeah, you've got different levels of evolution on the Kardashev scale, so it's just like the actual development of entire civilizations. So I think we are type 0 because we're still burning fossil fuel and we're still relegated or still on one rock. And we're going towards type 1 with sustainable means of being able to extract energy as well as being able to extract energy from the sun. I think that's one of the predominant factors that governs where you sit on the Kardashev scale. Anyways, I didn't think this video was going to be 49 minutes long. And I don't know if my daughter saw this, it might be a little bit beyond what you're learning in grade 2 right now. But my intention was not to confuse anyone. It's absolutely not the intention. However, that being said, the intention was also not to dumb down the rationale which we think about the probability of life and then intelligent life existing in this galaxy and other galaxies. I think, consider the fact that this equation was conceived or was first written in 1961, I think the equation does a pretty remarkable job of what it's supposed to do. And the fact that it's now being used in different variations, such as the Seager equation, SEAGER, and it's used now to find exoplanets and is successful, says a lot. I am not also going to get into the conversation about what should be changed or added to this to this combined expression, because I'm still this is a way for me to wrap my mind around Drake's equation, and to my uneducated eyes, these two parts kind of just stick out, whereby if you either alter them, change them, replace them, or add something to the equation, then it would actually increase. It would increase the probability of it would be the right kind of modifications in my mind to the equation, but I'm in no capacity to be able to comment on that as of yet. So I don't know how useful this is. There are other videos on YouTube whereby you can get a pretty good understanding of Drake's equation in a couple of minutes, 4 minutes or less. The Wikipedia page is great. It has all the basic information for you to be able to wrap your mind around this construct. There is a tool on the website for BBC, which is the British Broadcasting Corporation. I think that's what BBC stands for. But that BBC has a tool. It's an interactive tool which you can play with in order to be able to figure out for yourself what the probabilities of this are when you start tinkering with the numbers. So as opposed to you trying to do this by hand, which some of you should try, depending on how many people actually watch this, or maybe all of you, but that tool is quite interesting. It's interactive. You just use the user interface that you click on the probabilities and you tinker with the probabilities and you'll be able to come up with n. So you can come up with a number based on how you modify each one of these variables, and it makes it very easy. So check out that tool if you're interested. But that's it. That's Drake's equation. 61, so 40, 58, 57. 57 years, still going strong. I don't know what else to say. Thanks for watching.